So first thing with acid base is to think about like what your general acid base reaction is. And so when I say general, I mean like in a very, very general sense, because anytime you have an acid base problem on the MCAT, your solvent is going to be water. So the first thing that's going to happen whenever you put an acid or a base into solution is that acid or that base is going to react with water. Okay, so you're never going to have like, for instance, if you say you've got like a really strong acid, let's say like HCl or something like that, that's never going to react with anything except water, because water is going to be just so, there's going to be so much more water in solution than there is going to be HCl. And so it's like HCl will react with water, and then water will react with whatever HCl is said to be reacting with. And that's really important, because whenever you think about like you mentioned like pKa of an acid or the Ka of an acid, those numbers are supposed to be talking about like a quality of that acid, like the strength of that specific acid. But in reality, all of these are like, well, pKa comes from Ka.
Yeah.
Right. And Ka is really just KEQ for a given reaction. But if I tell you, like, if I tell you to think about like the KEQ of HCl, what's wrong with that statement? Like, what's wrong with me saying something about the KEQ of HCl?
It's not an equation.
Exactly. Yeah. HCl is a reactant, but it needs to be reacting with something.
Yeah.
And so Ka is the KEQ of the reaction where that acid is reacting with water.
Oh, got it.
Yeah. And that is the most important thing probably about acid base that people overlook all the time. And like that's going to make a lot of progress just for you just right there.
I honestly don't think I was ever taught that.
Yeah, probably not. So the Ka of an acid is the KEQ of the reaction between that acid, whatever that acid is. So we're just going to say HA, like where A negative is the conjugate base.
Yeah.
And water. All right. So we've got our general acid reacting with H2O. All right. And so the Ka of this reaction, well, our product, first of all, is going to be H3O plus A negative, right? So our Ka of HA is just going to be equal to H3O plus times A minus, and then divided by, well, water is a liquid, so it doesn't go in there, right? It doesn't go into the denominator here. So it's just divided by HA. And so that's always the case. And
okay, I know that equation, but I didn't realize the like KEQ water part. Like I have that equation in my study guide. I like memorized that equation, but
yeah. So that's pretty helpful, right?
Yeah.
So then so do you know what? So H3O plus. This is a really important point for acid base stuff, because do you know what the Ka of H3O plus is, or hydronium? That's what it's called. But okay, so the Ka, so H3O plus is important because it is going to be, H3O plus is the weakest of your strong acids, or so it's like the cutoff for being a strong acid.
Okay.
So does that make sense when I say the weakest of all the strong acids?
Yeah, got it.
Yeah, so it's like if something is stronger than H3O plus, then it's a strong acid. If it's not, then it's a weak acid. So it's like that middle ground there. And also, and so conveniently, the Ka of H3O plus is what defines weak versus strong acid, because the Ka of H3O plus is 1. All right. And I'm going to prove that to you mathematically, because if I come in and I want to make H3O plus my acid, okay, so we're going to have that same equation that we just did, but now H3O plus is the acid rather than just HA. So we put H3O plus in solution, react it with water. What are my products?
H3O plus again, and then H2O, so it's the same thing.
Yeah, so it's the same thing on both sides, right? And so Ka being concentration of products divided by concentration of reactants has to be 1.
Yeah.
So like it's necessarily 1 because it's the same thing on the top and the bottom,
Yes.
right? So that's how you define H3O plus as a Ka of 1. And so it's like if your Ka is greater than that of H3O plus, well then we can put that into this equation, right? And I'll erase this. I'll make it look prettier again. But if HA is anything stronger than H3O plus, then your equation is going to lie on the side of products. Therefore, your Ka has to be greater than 1.
Yep. If it's weaker or a base, then I guess.
Yeah.
If we're going off of that definition, then it would be less than 1.
Yeah, exactly.
Okay.
Perfect. Yeah. And so then the other thing we want to think about here is what it looks like whenever you make water be your acid. This is really important. So this is called the autoionization of water. Autoionization of water. All right. So when water is your acid, what's that reaction look like? Well, you've got H2O plus H2O because, it's just the acid reacting with water. Right. And then that's going to form, well, since one of these is the acid and the other one's taking up, so the other one has to be the base, right? Then you're going to have H3O plus OH minus form. Okay.
Yeah.
And so the Ka, right? Because now whenever I say the Ka of this, I just mean the Ka of water, right? Is going to be equal to the Kb of water also, right? Because water here is both an acid and a base.
Yes.
Because to talk about the Kb, you just have to react a base with water. To talk about the Ka, you just have to react an acid with water.
And if that's
so here
the water's both, yeah.
Right. So here we're doing both. So the Ka and the Kb are the same thing because they're both H3O plus times OH minus over just 1 because you've just got water on the other side and it's a liquid.
Yep.
Okay. So which side do you think is favored in this case? Well, H3O plus is a strong acid. OH minus is a strong base. So those two in solution together, probably not going to work out. Like those are definitely going to react. So this reaction is going to lie overwhelmingly on the side of the reactants, right?
Yeah.
Okay. And so that number, and this is a number you just absolutely have to memorize. That number is 10 to the minus 14. Okay. And so, and because it's both the Ka of water and the Kb of water, they're both 10 to the minus 14. So because of that, we call this just the Kw. Because Kw is equal to Ka of water is equal to Kb of water is equal to 10 to the minus 14. Okay.
Yep.
So that number is really important because it defines this equation for us. This is maybe this might be I don't know. There's a bunch of important acid-base equations. This is definitely one of them.
Yeah.
I was going to say the most. I don't know what the most is. But so it's Kw is going to be equal to your Ka of an acid. And this is any acid. This isn't just water. So Kw is water, right? So that's the 10 to the minus 14. That's equal to the Ka of any acid times the Kb of that acid's conjugate base. Or you could say the Kb of any base times the Ka of that base's conjugate acid.
Yeah.
Right. Okay.
Got it.
Yeah. And so, all right. And again, all of that is just equal to 10 to the minus 14 because that's what Kw is.
Yes.
Okay. So now if I give you the Ka of any acid, let's just do this one for like HCl. Okay. HCl, what's the Ka of HCl? It's like 10 to the 6, I think. All right. So if we do this for HCl, now we just need to find out what the Kb of chloride is, right?
Yes.
Okay. So you've got 10 to the minus 14, that's Kw, is equal to 10 to the 6, right? The Ka of HCl times the Kb of chloride. So what's the Kb of chloride?
Just 10 to the 14th divided by 10 to the 6th.
Yeah, so it's 10 to the minus
10
14th.
to the minus 14th. So 10 to the 8th.
So it's 10 to the positive 6, right? And 10, so in order to do that's the same thing as saying 10 to the minus 14 times 10 to the minus 6, right? Because
so you just add those two together. So then it's
Yeah.
10 to the minus 20.
Right, exactly. Yeah, because
Yeah.
it was in the denominator. So anytime you want to move
yeah.
an exponent up, yeah, you just have to take the negative of that exponent, right? So it's
Yeah. So it would be
Yeah.
10 to the negative 14th minus negative 6, which is no, just minus 6. Yeah. 'cause
Yeah,
it's
yeah,
like-
you were right.
Got it. Yeah.
Yeah, 10 to the minus 20 is correct. Yeah, so that's the Kb of chloride. Yeah, so now what is a weaker base, or what's a stronger base, I guess I should ask? Chloride or water itself?
Chloride.
So water is a stronger
fair.
base than chloride, right? Because its Kb is 10 to the minus 14, whereas chloride, the Kb is 10 to the minus 20. That's a smaller number. So the greater the number,
Okay.
the stronger it is. Yeah.
Okay.
Okay.
Got it. Yeah.
All right. So let's find out what's the Kb of OH minus. And you have enough info to do this. I don't have to give you anything else. So Kb of OH minus. How would you solve that?
So I would do Kw is 10 to the minus 14th, which equals Kb times the conjugate acid,
Mm-hmm.
right? Which is just H2O.
Yep. Yeah.
Times H2O, or the Ka of
Mhm.
H2O. And we know the Ka of water is 1.
Ka of hydronium is 1. Ka of water is 10 to the minus 14, remember?
Oh, yes. Oh, I see. Yeah. So then it would just be Kb is equal to 10 to the minus 14th over 10 to the minus 14th.
Yeah, exactly.
14. So 1.
Yeah, exactly. So Kb of hydroxide, OH minus,
Mm-hmm.
is just 1. So hydroxide is the same thing for bases that hydronium is for acids.
Got it. Yeah.
For the exact same reason. So all of this is like self-evident mathematically. Yeah.
Yes.
Which I like, because you can literally derive it all from first principles. So it's like if you forget it on a test, you can just like rederive all of this.
Yeah.
I mean, if you like forget everything and are also like cool-headed and
have
like,
a lot of time. Yeah.
yeah. But it's not really that much time, right? If you think about this, that equation gets all of it for you. If you think about that, and then this detail, I think that this detail is the most important thing. The Ka, just like the definition of what the Ka is.
Yes.
Like that and this equation, just those two things in yellow get you everything on this. Yeah. All right. So let's do like one more, maybe.
Cool.
All right. So let's say HF. So Ka of HF is, what do you think the Ka of HF is? Actually, this is important to make some predictions on this stuff.
So the higher the Ka, the stronger the acid.
Correct. Yeah.
So HF is a weaker acid than HCl. So if HCl is 10 to the 6th, it would be like 10 to the 4th. I don't know.
So it's actually less than that. HF is a weak acid, period. So it's weaker than hydronium. So it has to be less than 1.
So 10 to the 1/2.
Okay, yeah, or 10 to the like, you'd say like 10 to the minus, yeah, because like 10 to the 1/2 would still be like 3.2, I think. Is that
Which
right?
is still a strong acid because it's greater than 1. Yeah. So 10 to the minus 2.
Yeah, okay, that's closer. Yeah, so it's actually and that's about as much as you could predict right there.
Yeah.
So how would you know that HF is a weak acid if you didn't just know it off the top of your head? Because you can predict it.
Is that like a periodic trends situation?
Yeah, it definitely
Okay.
is. Yeah, so all of the hydrogen halide acids, meaning like HCl, HBr, HI, all of those are strong acids except HF. It's the only one of those that's a weak acid, which kind of goes against what I was just saying. Unless you remember the fact that HF is, well, the F minus, so fluoride, is a very strong base. It's not a very strong. Okay, it's a weak base also, but it's a very reactive atom. And the reason is because it's only got 9 protons and it's carrying around a whole extra negative charge. So it's got 10 electrons and only 9 protons. And so that like -1 charge on fluoride is a lot more significant than a -1 charge on chloride, because if chloride has a -1 charge, it's got like 17 protons, right?
To balance, yeah.
Right, exactly. And 18 electrons. And so the difference of just 1 extra electron on chloride is a lot less significant than just than that same difference of 1 extra on fluoride, because it's like, it's like a 12% increase in negative charge on fluoride, whereas on chloride, it's like a 5% increase in negative charge. Right. And that gets even more significant for bromine, and then more significant for iodine. And that's why the further down that table you go in that same group, the more acidic these things get. So HI is a stronger acid than HBr, and that's a stronger acid than HCl, and that's a stronger acid than HF. And the reason is because the bigger the atom is, the better able it is to delocalize that just 1 negative electron.
Yes.
Okay, so they're just more. Yeah, go ahead.
As the atom gets bigger, it becomes a stronger acid. Is that correct?
Yeah, as the atom gets bigger, the conjugate base gets more stable. And as the conjugate base gets more stable, the acid becomes stronger.
Yeah.
Because when you're determining how strong an acid is, the only question you need to ask yourself is, how stable is the conjugate base? If the conjugate base is really stable, then it's a strong acid. If it's not, then it's not a strong acid.
Yeah.
Right. Okay, cool.
Okay,
so
got
HF, so the Ka of HF is like 10 to the -7, I think.
Cool.
All right, so what is the Kb of F minus?
So again, 10 to the -14 equals 10 to the -10.
Did you say 10 to the -10?
Mm-hmm.
Well, remember, it's 10 to the -14 equal to Ka of the acid, which was 10 to the -7, right?
Yeah.
Times Kb of the base. And so that ends up being 10 to the -14 divided by 10 to the -7, right?
So then isn't that the same thing as multiplying it times 10 to the +7?
Oh,
it's 14. It looks like a 17 on my sheet, but I do know that it's 14.
Gotcha.
And that was a dumb math error. So then it's 10 to the 7th -7.
Well, what did I do right here? Oh yeah.
Because it's
10 to the
negative on the
-7.
bottom, right? So then you just add -14 plus 7. Okay.
Yeah. There.
Yeah.
Okay, yeah. So it's 10 to the -7. So F minus is not actually a strong base, but it's also not, but it is a base. And so because it is a base, that means that the acid can't be a strong acid because the base wants to react with stuff.
Okay.
See what I'm saying? Okay. So, all right. So that is a bunch of stuff about like Ka. So how do you transition between Ka and pKa? So like, what's the pKa of HF? Would be a good question.
pKa of HF is the log of Ka. So the log of 10 to the -7, which is just -7.
Well, it's the negative log.
Negative
That's
log,
important.
so +7.
Yeah, exactly. Yes, because it's negative log of 10 to the -7 is -7, which is 7. Yeah. So the pKa is 7. So what's the pKa of hydronium? H3O plus.
hydronium is the Ka is 1.
Mm-hmm.
Right? Okay. So -10.
So -10 would be, if it were -10, then the Ka would be 10 to the power of 10.
Hmm.
Right? Because it's the negative log of 1.
Yeah,
so
the negative log of 1.
Yeah, what's the log of 1?
That's 10 to the what equals 1, right?
Yeah, yeah.
0.
Yeah, yeah, exactly.
Okay.
So -0 or 0. Right, yeah.
-0.
Yeah, yeah. So pKa of H3O plus is 0.
Okay.
Yeah. And that's the same as the pKb of OH minus.
Got it.
Okay. Yeah. And so there's another thing you can get out of this equation. I actually haven't thought of this before. This is literally the first time I'm saying this, but I could see it being useful. So this Kw equals Ka times Kb equation right here.
Mhm.
You can make a version of this for the pKa and the pKb as well, because you could just say, well, Kw is 10 to the minus 14, right?
Yeah, so then
Okay.
it's 14.
The pK of that would be exactly
Mhm.
14. And so you could say 14 is equal to the pKa of an acid plus, not times, but plus the pKa or pKb of the conjugate base. Why is it turned to plus instead of times? That's
Because you're doing exponent multiplication.
yeah, exactly.
So
Yeah,
you're
because
adding.
you're
Yeah.
using logs. Yeah. And that is where the pH scale comes from.
Yes.
Yeah,
That
I
I
hadn't
did
thought
know.
of this before. I don't know why nobody's ever said that equate. That's because it's true. It's right. Whatever.
Yeah.
Okay.
Well, yeah, I mean, it makes sense.
Yeah, yeah. So anyway, all right. So that's all of that stuff. Trying to remember. Okay, so you were wanting to talk about titrations and stuff, right?
Yeah, and can we talk about, like, when they give you, like, a pH or a pKa, how to go back and forth quickly and easily, if that's possible?
Yeah, yeah, for sure.
Okay.
Yeah, let's say, so you want so what do you want? The pK, so you're wanting to, like, they give us pH
Like,
or they give us
a lot
pK?
of times, like, they'll be like, or I think in this one problem that I had the question about, they were like, there's a buffer of this pH, like, or something, or like it needs to stay within this pH range. Like, which buffer would you use? And it was in pKa, not
Gotcha.
pH.
Okay. Yeah, yeah, yeah. So
And
there's
I've
this equation.
definitely seen that before, or other situations in biochem or chem where they want you to convert between the two.
Yeah, yeah. So one thing to be clear about specifically, this might be really helpful for this, just the same way as my Ka definition up here is helpful,
The
is
the
that
water situation, yeah.
yeah, that because it's the same type of thing where pH is a comment on the concentration of hydrogen ions present,
Yes.
right? And so pH is like an attribute of your specific solution that you have, whereas pKa is like an attribute of the acid itself. And so the pH can be various, like you can have really different pHs for a solution with the same acid because it depends on the concentration of your acid in that solution.
Can you
So
say that
like
one more time? Sorry.
yeah, I didn't it's a kind of a hard concept to state.
No, I
So
think you said it right. You just one more time.
yeah, so it's like okay, if I tell you you've got a solution of, let's say you've got one solution that has 0.1 molar HCl in
Oh,
it.
the pH can change. I see what
Mhm.
you're saying. Like,
Yeah.
yeah, we do this in lab all the time. We want a buffer of a certain pH and we just like add HCl in inconspicuously on the bench. We're supposed to do it in the hood, but
Yeah.
and the pH
Yeah,
changes,
I
but the pKa of HCl is still the same. I see what you're saying.
yeah, exactly.
Yeah.
Yeah. So these two solutions will have very different pHs. even though
Yeah.
HCl pKa is always going to be -6 or whatever. So
I see. Okay.
mhm.
So like pH is effectively the acidity or basicity, I don't know how to say that word, of a solution, where pKa is the acidity of a like compound.
Yeah, pKa is going to be a comment. pKa is telling you how easy it is for that acid to give up its proton. And pH
Yes.
is telling you what the concentration of hydronium in the solution is. That's specifically what pH is. Okay, because
Okay.
pH is the negative log of pH is the negative log of the hydronium ion concentration. That's really what pH is. That's the actual definition.
Yes, and the pKa shows you like how easy it is effectively to get the hydronium ion.
Yeah, exactly. Yeah, so if you've
Okay.
got a stronger acid, you need less of a strong acid to get to the same pH versus a
Yeah.
weak acid. So it's really important for your body to be able to maintain a pH of 7.4
Yeah.
for a lot of different reasons. Mostly because you're made up almost entirely most of everything that's functional in your body is a protein. Like the proteins in your body are really, really crucial for staying alive. And as you deviate from their optimal pH, they stop working, right? So your
Yes.
enzymes stop working, you fall apart structurally. It's a really bad situation. So it's very much in your interest to maintain a pH of 7.4. However, basic metabolism is constantly generating acid. And so you need to have a buffer that keeps your pH at 7.4, otherwise you die. And so the buffer and so what we've done, or what our bodies have done, is kill two birds with one stone, because we also have carbon dioxide as the primary metabolic byproduct of all of metabolism. And so
Yes.
what we've done is because we need to transport that carbon dioxide from the cell where it's made, anywhere in the body, out of the body via the lungs. But carbon dioxide, being a nonpolar molecule, is really insoluble in the blood. So what we've done is turn it to be a soluble form in the blood and use that also as a buffer system. Okay, so
The
it's kind of a neat.
bicarbonate, right?
Yeah, exactly. So what you're able to do is take CO2 plus H2O, and you have this is an enzymatically catalyzed reaction. It's catalyzed by carbonic anhydrase. This you actually do have to know for this test and forever, just because like this is hugely important. I would learn this because it's like gonna be tested on the MCAT probably, and over and over and over in med school. Okay, so
What is that? Carbonic anhydrase.
yeah, carbonic anhydrase. Okay, so it catalyzes this reaction to form H2CO3 from that. Okay.
Yeah.
H2CO3 then is kind of a weak acid. I think the pKa is like 6. Is that right? Yeah, that's right. So the pKa is 6-ish. Maybe I think it's like 6.5 actually. So pKa 6.5 of bicarbonate is the name of that acid. Or no, carbonic acid is the name of that acid. And so it will dissociate in water. Let's show the actual reaction. So it reacts with water to give water the proton, right? Just like any acid-base reaction. And it's left with its conjugate base, which is bicarbonate. This is bicarb.
Yes.
All right, cool. Okay, so if I tell you the pKa of carbonic acid is 6.5, then then what's the Ka of carbonic acid?
pKa is 6.5, so that is the log of the Ka, negative log of the Ka. So it's 10 to the minus 6.5.
Okay, yeah. So yeah, exactly. So the Ka is 10 to the minus 6.5. And we'll just leave it there for now. We won't simplify it further. Although we can do that exercise if you'd like, but I think it's probably fine to just leave it for now. All right. So yeah, and minus. Okay. And so that 10 to the minus 6.5 is equal to the concentration of
hydronium.
Yeah. times the concentration of your conjugate base divided by the concentration of the acid. Right? Okay. Cool. So then the buffer system that you end up with. So basically the consummate question, and this question comes up constantly, like the exact same question. All right. So
fantastic.
yeah. So the question is going to be like, what is the ratio of bicarbonate to carbonic acid at pH 7.4? Like at physiological pH. Yeah.
Yeah.
I'll even write it right here. I think the MCAT should start putting 3 question marks at the end of all their questions.
It would make it more exciting.
Yes, exactly. I like that. It'll make it more exciting.
Okay. Ratio of so we can do the same thing we did before, right? With the more complicated problem.
Yeah, exactly. Yeah, because that's the question, right? What is the ratio?
Yeah.
Yeah.
So we have pH equals 7.4 times the pKa of, start with carbonic acid, which is so times 6.5, or sorry, 7.4 equals 6.5 plus the log of the concentration of the conjugate base, which is HCO3 minus.
Yeah, but you don't even need that right now. See how I keep writing log of answer, right? Because the ratio is the answer.
Yeah, no, that's right. Okay. I'm gonna.
Because they will. That's how they ask it all the time. It really is.
Oh, that's really annoying of them, isn't it? So it's just HCO3 minus over H2CO3.
Yeah.
And this equals ratio equals answer. Got it. Cool.
Yeah.
So then it's 7.4 over 6.5 equals log of answer. So then
wait, not 7.4 over 6.5 though. 7.4 minus
6.5, which equals what, 0.9?
Yeah.
9.
Which is basically 1.
Which is approximately 1. So then it's 10 to the 1, which is 0, equals, okay. So 10.
Wait. 10 to the 1 is what?
10 to the 1 is 10.
10. Yeah.
10 to the 0 is 1.
Yeah. Okay. You said 10 to the 1 is 0. That's why I was saying that.
Yes, but 10 to the 1 is actually 10.
Yeah, 10 to the 1 is 10.
Okay,
Correct.
okay. So the answer is 10.
Yeah, exactly. Yeah, so answer equals 10. So that means that you've got 10 bicarbonate to 1 carbonic acid at that pH.
Yes. We have 10 bicarb to 1. Yes. Yeah.
And so generally speaking, this is just like kind of a rule of thumb. A really good buffer is going to be within plus or minus 1 so if you want to buffer your pH at a certain number, a good buffer system is going to be one that has a pKa of plus or minus 1 from that pH that you want to buffer.
But the pH So the pH is the solution.
Yeah.
So we want a pKa that is plus or minus 1 of the pH.
Mm-hmm.
So if the pH is 7, we would want a pKa between 6 and 8.
Yes, exactly. Yeah.
Okay.
And this one is particularly even better than that because this is a buffer system that's more buffering against the notion of your blood pH getting too low than too high, right? Because the pKa is below the pH that you're looking for, right? But the reason that that's really good is because there are no internal mechanisms for your blood to get more basic than 7.4. Your blood is going to trend toward being more acidic than 7.4 because the byproduct of metabolism is acid, right?
Yeah.
And so the fact that this falls on that side of it is particularly good.
So that the pKa of carbonic acid is lower.
Yeah.
So it's more acidic. Less acidic.
Yeah. Well, it's just lower. Yeah, it's hard to say. Yeah, I mean, it's like the carbonic acid dissociates at a lower pH. So therefore, at a lower pH is already producing the bicarbonate to buffer against the blood pH going up. Does that make sense? Or I'm sorry, to buffer against the blood pH dropping.
Yes.
Right? Because
so
our answer being 10 tells us that we've got more of the base than we do of the acid present at physiologic pH. That means we're more buffered against becoming more acidic than we are against becoming more basic. Yeah.
Okay, that makes sense. Yeah.
Yeah.
So more base than acid at physiological pH. So more buffered against becoming more acidic.
Yes. Yeah. Okay. Precisely. Yeah. Which is helpful because that's the way that it would trend. Like if you stop breathing, you're going to get more acidic.
Yes. Okay. More buffered. Got it. Okay. That makes sense.
Okay, cool. Yeah. So yeah, that's helpful. And then, the idea of titrations, because for me, I don't know about you, but for me, whenever I was learning this stuff, like whenever I was prepping for the MCAT, titrations sucked. Like, I don't know why. I just couldn't conceptualize titrations in my head. And so I just but by default want to help people with these because it's something that I've found to be difficult for a lot of people, myself included. All right. So you can do titration one of two ways. You can either have, if you've got like an unknown acid in your solution, you can titrate that out with a strong base, or you can have an unknown base in solution and titrate it with a strong acid. Either way, you want to use a strong acid or a strong base as your thing you're titrating. And so
as the thing the thing you're titrating would be like the thing in the beaker.
Yeah,
or
so
the thing that's going into the beaker.
I don't know that my definition was precise either. The important idea is like the strong acid that you're bringing in. So like if you've got a thing that you know is acidic already, then you want to put individual drops of strong base in there. If you've got a thing that you know is basic already, you want to put individual drops of like HCl.
Yes, of a strong acid in there. Okay. So it's when you're saying the thing you're titrating, you're saying the thing in like the burette that you're dropping into.
Yeah, and I think I was saying that incorrectly. I'm not sure that was, and it doesn't matter.
I honestly don't even know. Yeah, whatever. Totally
and it's
fine.
irrelevant.
Perfect.
It's totally irrelevant. So so the most important thing, I think, maybe, or one of the most important things to be aware of in a titration is what your axes actually are. Well, any graph on the MCAT or in the world is
generally,
you really want to know what the axes are. Otherwise, you're just not going to get anything out of it. So for these titrations, you're going to have pH on your y-axis, and on your x-axis, you're going to have moles of either acid or base added. So let's say that we start out with an unknown quantity of a certain base, okay? Or of a certain acid. Let's say unknown quantity of a certain acid. So we're going to say moles of NaOH added. So moles of strong base added.
Added to unknown acid.
Right, yeah, added to unknown acid. Okay. So at the beginning, we have 0, right? So we haven't put any in, and so our pH is going to be also 0. Up here, pH is 14, meaning that we dumped a whole bunch of NaOH in there. So, yeah. All right. So I'm going to go ahead and put a couple more numbers on here just to make this easy for us. That way we can be aware of what we're drawing, what I'm drawing. Okay, there. All right, so now we know what we're dealing with. All right, so if we know it's acidic, that means it's going to start out at a really low pH. And as we drop NaOH in, what's going to happen the first time you drop NaOH in?
It is going to, if it's an acidic solution, there's an excess of protons, so it's going to react with the proton.
Exactly, yeah. And so it's
Okay.
not going to react with the acid, right? It's going to react with hydronium. That's
Because
That's really important.
theoretically freestanding, well, if it's a strong acid, there's hydronium in the solution.
Yeah, yeah. So let's actually just say that this is going to be, let's say that it's H2CO3 in here. Okay, so we know what's in here. All right. So H2CO3 is in the solution, and we've got
unknown acid. That's the unknown acid that's now known.
Yeah, or I'm just telling you that way we can just think about it this way, and we can do another one if you want. But so H2CO3 reacts with water, right, to form hydronium and bicarbonate, right? And then you can also take that bicarbonate, because this is a diprotic acid, right? Because HCO3 minus then will react with water again eventually to form more hydronium and CO3 2 minus. Okay, so we've got two different reactions that this thing's going to have happen, but you might be able to predict this version here, the second one, is not going to happen at a low pH, right? Because you're going to have a whole bunch of concentrated acid in solution. And so this thing isn't going to exist at all in solution until you get a much higher pH.
Because you have to go through the first proton first.
Right, exactly. Yeah. Yeah, because what's going to happen in this thing is that initially, like whenever you're at a really low pH, and we can do this calculation actually. So let's say we start this thing off at a pH of 1, okay? So if we look at that equation that we were just using, pH equals pKa plus log of, and we'll put HCO3 minus over H2CO3, right? If our pH is 1 and our pKa, I think you said it was like 6.5, right? 6.5, then that tells you that we've got negative 5.5 is equal to log of that ratio. I'll just put ratio. And so what that tells you then is that you've got 10 to the negative 5.5 of the thing dissociated for every one of them that is associated. So like all of that acid is all of that acid is associated at that point, right? There's none of it that's been really dissociated yet. And
so you need a lot of acid to have get the second proton. Is that what you're saying?
Oh yeah, but we're not even, just ignore the second proton for right now.
Okay.
So right now we just want to think, all right, we've got H3O plus in solution, right?
Yes.
We have to because the pH is low.
Yes, but then can you explain the 10 to the negative 55 one more time and what that means?
Oh yeah, sorry, the 10 to the negative 5.5 is just telling you that you've got 10 to the negative 5.5 of, you've got 10 to the negative 5.5 dissociated acid, right? So 10 to the negative 5.5 of it has lost its proton.
So that would be HCO3.
Yeah, for every one H2CO3 present.
Yes,
so what that's telling you is like all of our acid still has its proton on it.
Because 10 to the negative 5.5 is really small.
Yeah.
So you have most. Sorry, I don't know. I'm struggling with this.
Oh no, you're fine. Don't worry about it. Like this is somewhat difficult concept. Like
so you have 10 to the negative 55 means that for every one H2CO3, so the associated acid, you have 10 to the negative 55 HCO3. So you need a lot of the acid in the solution to get a substantial amount of the HCO3 minus.
Yes. Yeah. Okay. Yeah. Well, yeah.
Or high concentration. Yeah.
Yeah, because this 10 to the negative 5.5, you could also just say it's like, so 10 to the positive 5.5 is like 500,000 or something like that, right?
So it's 1 over 500,000.
It's like 700,000, I guess. But it's
yeah.
So well, I'm just saying if I flip this on its head, like if I
Yeah.
flip this ratio, then I could say we've got 10 to the 5.5. So this is 10 to the positive 5.5.
H2CO3
Mm-hmm.
for every 1 H2. Sorry, HCO3 minus.
Yeah, exactly.
Got it.
So
Okay.
yeah, so what that tells us is that we need 700,000 H2CO3 in order for one of them to dissociate.
Yeah, that's a lot.
Yeah. Right. Exactly.
Yeah.
Okay. So it's telling you like overwhelmingly these things still have their protons on them.
Mhm.
First one and second one. Okay. So as you start to add the strong base to the solution, each NaOH you add is going to take its OH minus. Each one of these that you add is going to take its OH minus and it's going to react that OH minus with an H3O plus.
Mhm.
And that's going to form 2 H2Os, right?
Yes.
Yeah, because you just got, you just take this negative thing, grab one of these protons, and then move on, right?
Yeah.
So it just forms 2 H2Os. That's going to happen for every single NaOH you add at the very beginning, all right? So initially, whenever we start adding NaOH, we get a pretty rapid increase in pH per NaOH that we add, because every single one of them is taking away an H3O plus. And keep in mind, pH is just negative log of H3O plus concentration.
Negative log of H3O plus. So that means as pH increases, H3O plus decreases.
Yeah, exactly.
Yeah.
Perfect. Yeah.
Yeah.
And I hate that the log scale really does make the negative.
Yeah, but I
log
mean, it
scale
makes
is like,
sense that as it becomes like a higher pH, so less acidic, there's less hydronium.
Yeah. Okay.
Yeah.
And so that's happening at the beginning. And that's like a 1-to-1 ratio. Like every time you put in an OH minus, you're going to be taking out an H3O plus effectively, right? You're neutralizing an H3O plus every single time. And early on, while we're still at a pH that's really far away from the pKa, because keep in mind, our pKa of our acid is 6.5, right? So while pH is still way lower than pKa, the acid isn't going to come help at all right? But then as our pH gets close to the pKa of that acid, now every time we take away an H3O plus with our OH minus, that H3O plus is going to start getting replaced by our acid as we approach the pKa.
Okay.
So that means that so we add an OH minus, it takes away an H3O plus, and early on the acid doesn't care. So like as you approach the pKa of that acid, it starts to donate protons, and so adding an NaOH at that, once you get near the pKa of the acid, doesn't decrease the pH anymore. Or I'm sorry, doesn't decrease the H3O plus concentration anymore. Doesn't increase the pH anymore, because that H3O plus that you take away gets automatically replaced by the acid. So the acid is like this reservoir.
You're approaching the pKa.
Yeah, because the acid is like this reservoir of H3O plus, it's like this reservoir of H3O plus that doesn't get realized until we get near the pH where that acid wants to dissociate.
Which is the pKa.
Yeah, because the pKa is the pH at which the acid is 50% dissociated.
Yes. So as we're adding base here, I'm now getting confused again. So we're adding base until we hit a pH that is close to the pKa of the acid.
Yeah. And we keep adding base.
Yeah, so we're adding base, like the base just continues to be added, and it keeps neutralizing the hydronium ions until we get to the pKa of the acid that's in the solution. Is that correct?
Yeah, of that.
Confused then. Okay, so now I'm confused. What happens then? So we're at the pKa.
Yeah.
We've added enough base to get to the pKa of the solution where the acid is dissociated 50% of the time.
Yeah, or so we haven't quite gotten to that point yet. So as we get near that pKa, our addition of more base doesn't change the pH as much because the acid is replenishing the H3O plus that we are taking away with addition of our base. So, early, every
I
time
see,
we
because it's
move to the
closer to
yeah,
its pKa where it's dissociating.
right. And so
Okay.
early on, we remove a bunch of H3O plus, like our slope is pretty steep, this being pretty steep early on. But then as we get near the pKa, our slope gets less steep because near the pKa, addition of more base isn't going to change the pH at all because that hydronium that we remove with addition of the base gets immediately replenished by the acid.
Because the acid's dissociating.
Yeah. And so
Yeah.
how long this thing stays flat depends on how much acid we have present.
Okay.
So eventually we deplete the acid. As we end up adding more and more NaOH, eventually we run out of H2CO3, right? And so our pH will start to creep back up again. So our slope will start to slowly increase again, right? As we get further from that pKa. And then so like if this were just a monoprotic acid, meaning like if it were like HCl or something other than H2CO3, then it would just go like that off and we'd be done. But
because
since it's
we'd
a
have
diprotic acid,
more. So what would happen then? So that's saying that all of the acid has reacted and become dissociated, and the pH shoots up because the base just neutralizes it.
Yeah, because now we're back to the same. We would basically just get back to the same slope that we had at the beginning, where we were just 1-to-1. Every base we add removes a hydronium, right?
Yes, but then once all the hydronium's gone, then we just have base.
Yeah, then we're at pH 14.
Yeah. Okay.
Yeah.
Got it.
Because pH 14 means there's no more hydronium left.
Yes.
Okay. So, but because we have a diprotic acid, we have the second pKa that we need to worry about. So pKa1 is 6.5. pKa2, I don't know what it is in real life. Let's just say it's like 11. Okay. Who cares? But we just need to like an example. Okay.
So, and that's where the where is it? The HCO3 dissociates.
Yeah, it's where this reaction happens, the second one. So this is pKa1.
Yeah, and then pKa2.
And then this one over here is pKa2 equals whatever it was, like 11, I think. Yeah, I think
11,
11. Okay. So, so at that point, so in between them, our slope gets pretty steep again because the first one runs out of protons before the second one starts to get dissociated. All right, but then once we start getting close to that 11, then the same thing starts to happen again. Our slope flattens out a bit, and then eventually we use up all of it, and so the slope goes back to being steep.
Yeah, and at that point we just have all base because we've used up both protons on the acid. Okay.
Yeah, exactly. And so you have these 2 points at the steepest parts of your graphs. See, these 2 points are called the equivalence points at the steepest part. So we could just call this like the first equivalence point, right? Because if it wasn't a diprotic acid, we would only have one equivalence point. But so the first equivalence point symbolizes that now we've added. So equivalence point tells us this is the point at which we have added as many moles of base as we have moles of acid present.
Okay.
Yeah. So equivalence point says moles of NaOH added. And we could also put it as a ratio divided by moles H2CO3 present equals 1.
Got it.
Yeah, and so then the same thing would happen over here at the second equivalence point. And you could say it's like that it equals 2, or you could just say there's like a 1-to-1 as well with moles. I guess you'd have to say it equals NaOH divided by originally, like the moles of H2CO3 you had originally is equal to 2. You see what I'm saying? Or you could say like moles
Yeah,
of
so that equals 1 or equals 2 or would equal 1 if you're going off of HCO3.
Yeah, exactly, precisely. Yeah, I just wanted to make sure that wasn't a point of confusion for you. But
got it.
Yeah, so the equivalence points are the steepest points on the titration graph.
Steepest points on the titration. Okay.
And then the other 2 points you want to be aware of are right here and right here, the flattest points.
Yes.
And so what these are is the 1/2 equivalence points. One-half equivalence point is the point at which the pH is equal to the pKa. And so that also means that's the point where the buffering capacity of the solution is the greatest.
So that's the point where you're matching effectively equally the base, so the OH to the HCO3.
Yeah, yep.
Okay, so that's the point where you're getting like a 1-to-1.
Yeah, that's the point where it's like every mole of OH that you add, or every mole of NaOH that you add, is deprotonating a mole of H2CO3 or mole of HCO3.
Yeah.
Which means that the pH is no longer increasing because the acid is, because your buffer system is doing its job.
Yes, got it.
Yeah. So that's how the titration. That's one of the hardest things to explain, in my opinion. It's very difficult.
Yeah, and that makes a lot more sense now. I think I'll rewatch the video a couple times and
Okay, cool.
Yeah, make sure I understand. But yeah,
Yeah,
that makes a lot of sense with the titration and generally the Ka versus pKa versus the pH and how to go between. Makes sense.
Okay, cool. Yeah, because I think that's pretty much like it for acid bases. Like we just covered everything on acid bases.
Yeah. I will go through it and try to hit a few practice problems between now and Monday. And then if I have more questions, ask on Monday, but I think I have a much better understanding. It's just like a little confusing still, but
yeah, no, for sure. Yeah,
well,
I was gonna ask if you wanted to pull up that practice question that you had that you were talking about, and then look at it now after having talked about this.
Well, let's do it. It was on my practice test on March 1st. Let me open it. What is it? What is this one? It was 403183. I'm finding it.
What was the test ID?
The test ID was 246-238-677.
And which question was it?
403183.
All right. Or what actual number? It's a little quicker.
7.
7. Okay. Yeah, that's a little faster. Because if I have the test ID, then it gives me all the
8
same
numbers.
questions.
Yeah.
All right, nice.
Okay. I think I understand this now.
Okay. The same, which of the following titration curves corresponds to the amino acid found at peak 17 of the chromatogram? Okay, yeah, so you have to find peak 17. Saying lysine?
So peak 17 is lysine, so you have to know the structure of, I guess not even, it gives you the pKa, so it gives you the lysine side chain, and then you have the N-terminus and C-terminus, which would be where the pKa, or which would be where you're losing protons again, right? Yeah. So then the pKa of the C-terminus is at the lowest point, so that would be like where the graph is at like 2.2, and then you would go do 9.3, and then of the lysine side chain is 10.5. Yeah, that's easy. I got that now. That makes a lot more sense.
Because it does give you that chart. That's nice of it. Yeah.
It gives you the pKa chart. Yeah. So do you need to know the pKas of the amino acids? Okay.
Unfortunately, yes.
fun. Good.
Yeah. Yeah, it's kind of ridiculous. It's really honestly very ridiculous, to be honest. Like, I think that that's one of the stupidest parts of the MCAT is some of that memorization.
Like,
that you
I
have
know
to
the
do.
amino acids, I just don't know the pKs of
Right,
the amino
yeah.
acids and the side chains and the groups. But that's a nice little chart.
Yeah,
I'm gonna
and
take
generally
a
speaking,
nice
you can kind of
screenshot of that.
yeah,
Like
that's true.
based on how acidic the like if it's an acidic amino acid or
Mhm.
yeah, and I mean the pKa of the C terminus is lower
Yeah,
because that proton's easier to grab.
right.
Right. Okay. That's not correct terminology, but that's going to be more stable than if you take it off of the N. So it's going to be higher. And then the side chain of the lysine. I see. Okay.
Yeah, and so if it's a basic amino acid like lysine or one of, I don't know, the others, tyrosine is one. Well, I mean, they have it listed there. So arginine. If it's one of those, then the pKa of the R group is going to be closer to that of the N terminus. And if it's a basic amino acid like glutamate, then it's going to be then the pKa is going to be near the C terminus one. And then one other, while we're on this topic, do you know how to find the pi of a given amino acid?
The isoelectric point, right?
Yeah.
No, but I think, is there an equation for that?
I think there is, but you can also just like conceptually think through it this way. So it's like the pi of an amino acid that doesn't have any acid base activity on the R group. So one, like, I don't know, we could just say like glycine, for instance. Like glycine doesn't have an acidically active R group. So the pi for that is just going to be right in between the pKa. It's just going to be like right in between the pKa and the pKa of the N terminus and the pKa of the C terminus. Is where the pi is going to be for that.
Okay.
Does that make sense?
Can you explain what the pi is one more time?
Yeah, it's the iso. You said it. It's the isoelectric.
Yeah, no, I know. I just don't know what that means.
So it's gonna be.
I think you said it. I just.
Yeah, it's the pH. It's the pH where the thing isn't charged.
Okay.
Yeah. It's it's gonna be the pH where you have neutral charge on the whole molecule. So it's like if you put it on a pH gel, then it's the pH where it's gonna stop. So like in a pH gel, you'll have like a positively charged side and a negatively charged side, and then you set up the pH, and then you have like this pH gradient set up, and then I have to think about it. So positive side. Okay, so you want your pH 14 on this end, pH 0 on this end. And then so like the amino acid is you just drop everything on this gel and turn it on, and the amino acids are going to migrate as they are charged. Yeah.
Okay, and where they stop, that's where it's a neutral charge. Got it.
Yeah, because it's going to get more protonated as it moves toward the left, and also pulled more like negatively charged ones will be pulled toward the left. And so there's going to be a point at which it becomes neutrally charged, and as soon as it's neutrally charged, the current moving through the gel doesn't affect it anymore, and so it just stays put at the pH where it's neutrally
that makes
charged.
sense.
Yeah, so the
Okay,
pi.
So to find that without a pH gel,
well, you have to know the pKa's of the two groups or the three groups.
So you have to know the pKa of the C terminus and the side chain.
Yeah, and the R group. And so like you don't have to know, like, so you're gonna need to know the pi of every amino acid. That's something just to memorize for this test, which sucks.
Okay.
It's
I can do that though.
Just
there's only 20.
Incredibly stupid though that you have to do that.
So memorize pi of the side chains.
No, of the amino acid.
Okay.
Just so I'll find a table. I'll just put it in here right now.
Memorize pKa of the N terminus, C terminus, and side chain as well.
Well, no. So you just need to know the pi, but I was just telling you like how to find the pi, because then you could reverse engineer it, if you needed to. So here's a table with all of it.
Nice. Thank you.
So, no problem. So what I was just going to say though, like, so since you'll know the pi going in, then you can calculate any of the other stuff if given a piece of the info, because all you need to know to calculate the PI is, well, you could either know like what the pKa of the C terminus and the N terminus is for something like glycine, or if it's something like glutamate that has, 3 pKa's involved in that amino acid, then you just need to pick the two that are the same, right? So if it's like an acidic amino acid like glutamate, then you want to pick so you take the two that are the same and you figure out the average between the one that is different and the one that is closest to that. And I know that that's like a stupid way of saying it. So let's just look at it for glutamic acid right here. Yeah, because that was a terrible way of saying it. So you've got your pKa1, meaning like your C terminus, right? So your C terminus is going to be neutral at 2.2. Okay, pH 2.2, right?
Yeah. Wait.
Because that's its pKa.
That's its pKa. Okay, yes.
Yeah. Yeah, so pKa is just saying that's the pH where we're neutral, right?
Yes.
Where 50% is dissociated, okay?
Yes.
So then you have the R group, which has a pKa of 4.3. I'm just rounding. There's 4.25 over there. And then you have your N terminus with its pKa of 9.7. Okay. So in order to find the PI of glutamate, and I'm scribbling it out over here, then you just want to, so all you have to do in order to find the PI of glutamate is just find the pH, find the two that are alike, right? And so since glutamate is an acidic amino acid, that means that the two that are alike are the R group and the C terminus. Okay. So you just find the two that are alike and then average them. And that's all.
Okay.
Yeah. So the average of 2.2 and 4.3, well, we add those together, 6.7 divided by 2, 3.35.
Yeah.
3.22. Yeah. So
like close enough.
Yeah, that's plenty close for the MCAT.
Yeah. Okay. Yeah, that makes sense. So then if you could just do that reverse, if you know the PI, you could then figure out the pKa.
Yeah, exactly. Yeah. So yeah, if they give you the PI or the PI already and they tell you the pKa of one of the groups, then you can figure out what the pKa of the other
one is. Yeah. Okay.
Yeah. And that's helpful for identifying like a mystery amino acid, for instance.
Yeah.
Yeah, I know. But that's the kind of that they ask on the MCAT. So
yeah, because that's like exactly what you need to know to be a doctor.
Yeah, I was about to say, yeah, that proves that you're apt to be able to do surgery on somebody in 10 years.
Oh yeah.
Yeah.
You can determine this.
Yep.
I'm just trying to see if there's any other that I had questions about. I think that was okay. I had other questions, but I also should probably go study on my own soon.
Yeah, totally up to you.
I don't want to necessarily open another can of worms. Because that was a lot of acids and bases.
Yeah, we definitely covered a lot of acid-based stuff tonight. I'm happy to answer. I have nothing else I have to do.
Okay.
So I'm happy.
Can you give me like 1 second just to see if there's something that's like quick?
Oh yeah, for sure. I'm gonna go grab some water really quick. I'll be right
take
back.
Your time. Okay.
Okay, thanks.
Okay, so this is actually kind of a general orgo question. So like when you have like a sugar, or I think the sugar, and it's like linear form, and it's like makes a circle, cycle something, and there's the anomeric carbon.
Yeah.
Can we go over that, and like if it's like a complex molecule, like how you figure out which one it is? Because I feel like that comes up a lot where it's just like a question that seems really complicated, but if you know which one's the anomeric carbon, then it's like very clear.
Yeah, for sure. Okay, yeah. So let me try to. Okay, so
and I might cut myself off at like 9:15 or 9:20, and then
we should
just
be
so
able
I can have enough time to do other more practical problems tonight.
Okay, cool. Yeah, and we should be able to get it done by then.
Yeah.
Okay.
I also like roughly know it. I just am always like I had never heard that word before I started studying for the MCAT. Like, that was never something we covered in Orgo, which feels stupid that we didn't cover it, but
All right.
or I just
So
completely forget it, which is also highly possible.
okay, so whenever glucose forms its cyclic form, this thing right here, right? It's this oxygen that comes up and attacks the carbonyl carbon, right?
Yes.
Okay. And so that causes this O8, this carbonyl to turn into just an OH, right?
Yeah, because it'll just pick up the hydrogen from.
Mm-hmm.
Yeah. Okay.
Yeah. So when that happens, what we do, we go from having, so how many chiral centers are there in the glucose molecule prior to that reaction? There are 4, right?
Yes, because
Okay.
the other ones, yeah.
Yeah. So there are 4 chiral centers in glucose prior to that reaction. However, whenever that attack occurs, it takes this carbon that wasn't chiral before and makes it chiral.
Yes, because now it will be attached to 4 different things as opposed to the
Mhm.
double bond. Okay.
Yeah. And so depending on which side that oxygen that attacks comes in on, we can have the R version of that glucose or the S version of that glucose. And so the
Yes.
anomeric carbon, this is the anomeric carbon because it was not chiral and now it becomes chiral. And so whenever you introduce a new chiral center, what you're also introducing the possibility of an extra whole set of stereoisomers.
Yes.
Because I think this is D-glucose right here, right? And so if you have, I'm trying to remember if it's R, which one's R, which one's S between alpha and beta. Doesn't matter, whatever. We can look that up in
Yeah.
a second. So
Yeah.
yeah, if when that anomeric carbon forms, it has R configuration around it, then it will be alpha D-glucose, let's say. And maybe maybe it's S that's alpha. I don't remember. I'll look it up later.
Okay.
And if it's the other one, then it's going to be beta D-glucose. So that anomeric carbon introduces the possibility for two diverging versions of glucose. See what I'm saying?
Yeah, so you
Yeah.
can have either configuration
Yeah.
around that stereo center
Mm-hmm.
after it cyclicizes. You know what I mean?
Yeah. So you can create two totally different products from the exact same reaction on the exact same molecule.
Yeah.
Yeah, and so that's what that's all about. That's
Yes.
really it. And so the configuration around the anomeric carbon, once it becomes cyclical, like once we turn it chiral,
Yes.
determines whether the glucose is alpha or whether it's beta.
Yes. And that's the RS
Yeah, that's R versus
configuration.
S. Yeah.
R versus S. R is
Mhm.
the one of them's clockwise, one of them's counterclockwise.
Yeah, R is clockwise, S is counterclockwise,
S
and
is
so
counterclockwise.
yeah.
You could have alpha or beta, like D-glucose.
Mhm.
Okay.
Yeah. So
That's
it's gonna
determined
be
by if it's R or S around the anomeric carbon.
right.
If it's
Right.
alpha or beta D-glucose, and then D versus S, right? D versus L, D versus L, R versus S.
Yeah.
Then you could
So
also have L-glucose
mhm.
and then alpha or beta, depending on the orientation or
Yeah.
okay.
Yeah. So the introduction of a extra chiral center opens up the possibility for two different versions of D-glucose and two different versions of L-glucose. And those two different versions are the alpha and beta version.
So it just gives you the anomeric carbon is the carbon that becomes chiral, and the R versus S
Mhm.
configuration of that chiral carbon would then determine if it's alpha or beta.
Yep, exactly.
Okay, that makes sense.
Yeah,
Got
and
it.
that's really all there is to it.
Okay, and it's
Which
that carbon where it'll have an OH directly attached. I'm just trying to see how you like identify it in a molecule.
it
It's
would have
in
to
the
look.
ring. It's
Yeah.
in the ring. Yeah.
Yeah, you'd have to have wedges and dashes to do it, I think.
Okay.
Yeah, because it's gonna be like if you have you have glucose. Glucose looks like this most of the time, with another carbon like CH2OH coming up right here. And so that tells us that so this is the one that's attacking. So this is the carbon that's changing. And so, and so you're going to have like an OH and an H, and depending on which one's up and which one's down, that's going to tell you if it's alpha or beta.
Yeah. Okay.
Yeah.
Because it's the one next to the oxygen in the ring.
Yes. Right. Yeah. Yeah.
Yes.
It's the one that, it's the one that's directly attached to the oxygen that doesn't have the CH2 off of it.
Yeah. Okay.
Yeah. Because this and this are the same thing. They have to be. Everything else is the same.
Yes. Yes.
Everything else is interchangeable.
Yeah. Okay. Next to the oxygen in the ring, no CH2.
Yeah. Exactly. Yeah. Or
you want to just really brute force memorize it. That's the.
Yeah, because they're also going to be labeled like this: C1, C2, C3, C4, C5, and so it's going to be C1. It's like the configuration around that first carbon because it didn't used to be chiral and now it's chiral.
Yes, got it.
Yeah, and so anomers are. So what anomers are? So do you know what it means for two molecules to be enantiomers of one another? First of all,
non-superposable mirror images. No, that's diastereomers. No.
Yeah.
That's diastereomers.
Okay, yeah. So like glucose, for instance, is going to have, well, let's talk about the linear version, this thing, before we have the ring. And let me know if you need to go because this is a little bit extra, but C1, so we've got these chiral centers. So C1 is not going to be chiral in the linear version, but the rest of these are all chiral, right?
Yes.
I think 2, 3, 4. Yeah.
Yeah.
Yeah, correct. Why did I label 1, 2, 3, 4, 5, 6? I don't know how that happened. I put one fewer carbon, whatever. Okay. Yeah. So in the linear version, this one's not chiral. This one's not chiral. The rest of them are chiral. All right. So, so if in order for them to be enantiomers, you have to have opposite configurations at every chiral center. Okay. So every single one. So like if this is R, this is R, this is S, this is R, just for instance, I'm just making things up. Then the only possible enantiomer of that would be one that is S, S, R, S.
Yes.
Right. If something were like S, 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 that's not an enantiomer.
Yeah.
Because while it's opposite here and here and here, it's not opposite here.
Yeah.
Okay. And so those two would be the blue and the green, for instance, here are diastereomers of one another, right?
Yes.
And so the reason I'm going into that is that so enantiomers have to have opposite at all chiral centers. Diastereomers have to be opposite at all -1 at least chiral centers. They have to be opposite at least one chiral center, otherwise they're the same molecule.
Yes.
But then anomers are diastereomers that are opposite configuration at only one chiral center.
I see. Okay. So that would be the difference between how it makes a circle.
Right. Yeah. Because D-glucose is going to have, like D-glucose, you've got the same configuration in all 4 of these, and it's only this one where alpha and beta differ from each other.
Yeah.
Yeah. So
okay,
alpha, yeah. Yeah. So they've got opposite configurations here.
Okay.
Yeah.
Okay. Yeah. Thank you. That helps a lot. And maybe next time we go over isomers in slightly more depth, I'll see. So that was like one of my questions as well.
Okay, cool. Yeah, I'm happy to do that.
And just like how to differentiate, because that always comes up as well.
Nice. All right. Yeah. Sounds good to me. I've got a good spiel on on isomers. Although I did just give you like the Reader's Digest version of it.
Perfect. So, yeah. But yeah, maybe. Yeah. Okay. So maybe let's start with that next time, if that's okay.
Okay. Yeah. It's totally fine with me. I'm happy to do whatever.
Okay. Awesome. And I will see you Monday.
Okay. Sounds
We're
great.
good for the same schedule, right? That's every week.
Yeah. I think it's still in the calendar. Whatever's in the calendar, I just kind of like live my life by whatever my calendar tells me to do.
I also do that. Yeah, we're good.
Yeah, it's in there for Monday. Cool. All right, sounds
All
great.
right, thank you so much. Have a good night.
Yeah, no problem. You too.